Good morning. We are Group 1 and today we will be presenting our Experiment 1 buffer preparation. To start, let's first answer some guide questions. Number 1, what is the biological significance of pH and how does it affect biological activities and functions? So biological activities and processes are sensitive to changes in pH. The activity of cellular components and biological macromolecules, such as enzyme, may also be altered if the pH deviates from the optimum range. The conformation of enzymes highly depend on pH levels due to the ionizable group with specific pKa values which are present on their structure. Alongside this, changes in pH would affect the resulting ionic interactions, which would then influence the enzyme's ability to recognize and bind to substrates. Number 2, give one physiological consequence when pH is not regulated in an organism. One example is acidosis, where the pH levels of the body fluids drop below what is considered to be normal value, meaning that the blood has become too acidic. There are two types of acidosis. First is respiratory acidosis, where the lungs are unable to remove carbon dioxide in the body and thus build up within the blood. Metabolic acidosis, on the other hand, is the inability of kidneys to remove enough acid or too much base in our body. Next, in buffer preparation, why is the observed pH different from the calculated pH? The difference in the observed pH and calculated pH is due to the temperature. The Ka, or the acid dissociation constant, is usually computed at 25 degrees Celsius. Thus, if a buffer is prepared at a different temperature, the Ka value will also differ, hence the pKa will also be different. pKa's are used in the calculation of pH, so it means that a different pKa value will lead to a discrepancy in observed pH and calculated pH of the buffer system. For the fourth one, what are the characteristics of a good buffer? A good buffer has its pKa is as close as much as possible to its pH for its buffer capacity to be maximum. As most biological reactions occur at near neutral conditions, the pKa of a good buffer must also fall between 6 to 8. So the buffer should also be highly soluble in water but not in organic solvents. It also should not be able to pass through biological membranes, as the buffer might be toxic to the cell and to prevent it from accumulating. Good buffers also have appropriate ionic strength or minimal salt effects in order to neutralize the acid or bases in a reaction. Lastly, it must be neither non-toxic nor non-reactive, which is stable enough to resist enzymatic or non-enzymatic degradation. Next, what parameters should be noted in choosing a buffer? As mentioned earlier, the pKa of the buffer must be within the buffering range of the solution within 1 unit of the target pH. The concentration must also be within the range that maximizes the buffering capacity, but at the same time does not interfere with the structure of other biomolecules. Other factors to also be considered is temperature at which the pKa varies, the volume of the buffer, its solubility, other possible interference with the reaction, and other determinants of chemical compatibility with other biomolecules. Lastly, in general, how long can buffers be stored? The shelf life of buffers depend on certain factors that can change its pH, such as its composition, absorption rates, the temperature of the storage, and other units that can contaminate the buffer. Commercially made buffers must be stored according to the instructions provided. It can generally last 1 to 3 years from its manufacturing date, which is then reduced to 3 to 6 months after opening. Acidic and basic buffers, on the other hand, must be properly stored in appropriate glasses to avoid the absorption of bases or acids that could contaminate the buffer. However, near-neutral buffers is prone to microbial growth, especially those that contain phosphates. To avoid this, the buffer must be kept at a refrigerated storage and maintain stock solutions of sufficiently high ionic concentrations.
To give you a refresher on when to use values such as pH, pKa, and Ka, let us first answer some sample problems. So first, the pH of a 0.02 molar solution of a monoprotic acid was measured at 4.6. What is the acid dissociation constant Ka for this acid? Since the pH was given, we can calculate for the H plus concentration and we can plug that into our ice table. And then we can calculate for the Ka, which we find to be 3.16 times 10 to the negative 9. Given that, what will be the effective buffering range for this acid? The effective buffering range is given by the formula pH equals pKa plus minus 1. And then since we already calculated for the Ka previously, we can just get its negative logarithm and then plug it into the formula for the effective buffering range. And we get a pH range of 7.5 to 9.5. Next, the Ka of acetic acid is 1.8 times 10 to the negative 5. What is the pH of a 0.10 molar solution of acetic acid? Since we are trying to look for the pH, it means that we don't know the H plus concentration at equilibrium. So we put that on our ice table by substituting the value for our H plus concentration with the variable X. And then we proceed with calculating the Ka, which we find to be x squared over 0.10 minus x equals the given value of 1.8 times 10 to the negative 5. And once we isolate x on one side, we find that it's equal to 1.333 times 10 to the negative 3. And then we can plug that into our pH formula, which is negative log of the value, and we get 2.88. What are the equilibrium concentrations of the weak acid and its conjugate base? So if we observe the ice table, we find that the equilibrium concentration of H plus and CH3COO minus are the same. So for the conjugate base CH3COO minus, its concentration is also 1.33 times 10 to the negative 3 molars. However, for CH3COOH, the equilibrium concentration will be 0.1 minus X. So plugging the value in, we find that the concentration will be 9.87 times 10 to the negative 2 molar. However, this change is quite negligible. So for future solutions, we can just use the initial value for the weak acid in calculating. So it will be easier for us. Finally, the apparent dissociation constant Ka for the dihydrogen phosphate ion at 25 degrees Celsius is 1.38 times 10 to the negative 7. What is the pH of a phosphate buffer solution containing 0.025 molars of potassium dihydrogen phosphate and 0.25 molars of sodium hydrogen phosphate? So since we are looking for the pH of a buffer solution, we can use the Henderson-Hasselbalch equation, which is given by the formula pH equals pKa plus the log of the concentration of the conjugate base over the weak acid. So given the acid dissociation equation below, we find that the weak acid is H2PO4 minus and the conjugate base is HPO4 2 minus. So if we use the Henderson-Hasselbalch equation, we can plug the values in, get the negative log of Ka, and then plug the concentrations of potassium dihydrogen phosphate and sodium hydrogen phosphate, and then we get the pH of 7.86. So to give you a summary of the concepts we just learned, the Ka is the acid dissociation constant. It is the equilibrium constant of the acid dissociation equation, and it is considered the true measure of acid strength because it is unaffected by the addition of water. It is an inherent property of an acid, and it helps us predict the behavior of a specific compound or functional groups given a certain pH in a solution. So a higher Ka will give you a higher concentration of H+. On the other hand, pKa is the negative logarithm of the Ka rather. So a lower pKa will give you a higher H+ concentration. The reason why we use pKa is it gives us a smaller range of values as compared to Ka. pH. It is the measure of the proton concentration. So it is the negative logarithm of the concentration of H+ ions in an aqueous solution. So the pH is a scale. It ranges from 0 to 14. But for strong acids and strong bases, they can exceed the scale. So for strong acids, they may yield values of -1, -3. And then for strong bases, they can exceed and have pH values greater than 14. So the reason why the Ka and pKa values are considered the better measure of acid strength is because, again, they are unaffected by the addition of water as compared to the pH, which is dependent on the concentration of H+ in the solution. And the concentration is given by moles over liters. So once you add water, it increases the volume of the solution, which therefore decreases the concentration of H+, which will alter the value of the pH, which is why we prefer using Ka and pKa for measuring the strength of an acid. In order to relate the pH to pKa, we use the Henderson-Hasselbalch equation, and it is used for calculating the pH of a buffer solution.
For the first question, would the dihydrogen phosphate and phosphoric acid system function as a good buffer at a physiological pH of 7.4? This system can be considered a good buffer if 7.4 is within its buffering range of pKa plus minus 1. The equation on the slide shows the dissociation of phosphoric acid into the different phosphate species, and as we can see, the dissociation of phosphoric acid to dihydrogen phosphate has a pKa of 1.97. So when computing for the buffer range of the given system, we get a range of pH 0.97 to 2.97. Since pH 7.4 is not within its effective buffering range, we can conclude that no, dihydrogen phosphate phosphoric acid system would not function as a good buffer at a physiological pH of 7.4. Instead, a better buffer system would be monohydrogen phosphate and dihydrogen phosphate, which has a buffer range of pH 6 to pH 8, since the pKa value as seen earlier is 7. This system is also commonly found in the cytoplasm of cells. For the second question, why can't solutions of strong acids be used as buffers? This is because strong acids completely ionize in aqueous solutions. For example, hydrogen chloride added to water would yield the hydronium ion and the chloride anion. If you remember how buffers work, buffering results from two reversible reaction equilibria between the weak acid and its conjugate base. So when a strong acid is added to a normal buffer, its hydrogen ions react with the conjugate base in order to generate the weak acid. And when a strong base is added to that buffer system, then the hydroxide ions will react with the weak acid to generate its conjugate base. That way, the pH can remain relatively the same since the sources of hydrogen and hydroxide ions are basically added to the buffer. However, because a strong acid will ionize completely, the addition of another strong acid will just increase hydrogen concentration since its conjugate base is relatively stable and unlikely to react. And when a strong base is added to this solution, then it will just neutralize the strong acid in order to yield a salt and water, therefore not fulfilling its function as a buffer to maintain a certain pH. For the third question, what is the pH of a buffer solution made by combining 0.05 m each of acetic acid and acetate? What will be the resulting pH upon the addition of 2 ml of 0.1 sodium hydroxide to 300 ml of the buffer solution? In order to get the pH, we use the Henderson-Hasselbalch equation. The dissociation of acetic acid to acetate has a pKa of 4.74. For this equation, the concentrations of the weak acid and its conjugate base are already given and are equal to each other, so we can just plug them directly into the equation. Doing this, we get a pH value of 4.74. For the second question, when 2 ml of 0.1 m sodium hydroxide is added to 300 ml of the buffer, we can write the following equation wherein acetic acid reacts with the hydroxide ion to form acetate in a 1:1:1 mole ratio. So the first step is to convert the concentration into moles, which we accomplish by multiplying concentration to the corresponding volume, yielding the value shown on the slide. After that, we compute for the moles of each component after the buffer fully reacts with sodium hydroxide. Since acetic acid and sodium hydroxide are used up in the reaction, we subtract 0.002 mol. And since acetate is produced in the reaction, we add 0.02 mol to its initial value. So the final amount of mol for each component is shown on the slide. After this, we convert moles back to concentration. Note that with the addition of 2 ml of sodium hydroxide, the new total concentration of the solution is 302 ml or 0.302 liters. So to get the concentration of acetic acid and acetate, we divide the values we computed for earlier by 0.302 liters to get the concentration shown in the screen. And lastly, to get the resulting pH of the solution, we use the Henderson-Hasselbalch equation using 4.74 as our pKa and plugging the computed concentrations into the equation. With that, we get a final pH of 4.75.
Now we'll be discussing the steps, methods, and calculations involved in buffer preparation. Buffer preparation begins with obtaining the necessary details for the target characteristics of the buffer. These include the pH, volume, and concentration. Then a weak acid appropriate to the buffer is chosen, especially based on its pKa value. Then the Henderson-Hasselbalch equation is used to calculate for the ratio of the weak acid and its conjugate base. This ratio is then used to calculate for the individual concentrations, and this is then the basis for the masses of the reagents. Note, however, that the specific calculations are dependent on the nature of the available reagents. These reagents are then weighed according to their calculated masses, and distilled water is added in order to dissolve them. Next, the pH of the solution is checked using a pH meter. If the pH is higher or lower than the target pH, 0.1 molar hydrochloric acid or sodium hydroxide can be added dropwise until the target pH is obtained. This solution is then transferred to a volumetric flask and filled with distilled water to the mark, depending on the target volume. Lastly, before the usage of the buffer, it must be mixed thoroughly or stored appropriately at 4 degrees Celsius. As mentioned earlier, certain steps and calculations are dependent upon the nature of the reagents. Specifically, if both are available in solid form, the calculation for the mass is simply the concentration times the target volume times the molecular weight. However, in the case that one of the reagents is in aqueous form, the formula for that reagent is different in that the stock solution concentration is utilized instead of the molecular weight. On the other hand, if both reagents are available in aqueous form, the modified dilution equation is utilized instead as shown here. Lastly, if only one reagent is available, sodium hydroxide or hydrochloric acid can be used to convert the existing species into the other species needed by the buffer. A sample of problem showing this method is seen here. So how many grams of glycine hydrochloride and sodium hydroxide are needed to prepare a 0.2 molar buffer solution at pH 3? Looking at the dissociation of glycine, we see that the pKa value closest to the target pH is 2.3. And at pH 3.0, we know that the forms of glycine that are present is the positively charged form and the neutral form. Thus, considering that glycine hydrochloride denotes the protonated form of glycine, we then need sodium hydroxide to convert some of this species into the neutral form. In order to do this, first, assuming a 1 liter buffer solution, we can compute directly for the mass of glycine hydrochloride needed. This is the target concentration, which is 0.2, times 1 liter times the molecular weight, giving us 22.29 grams. Then the Henderson-Hasselbalch equation is used to get the ratio and then the concentrations of the species, with neutral glycine as the conjugate base and positively charged glycine as the weak acid. Inputting 3.0 and 2.3, that gives us 0.0337 molar protonated glycine and 0.1667 molar neutral glycine. We then need to calculate the moles of hydroxide needed in order to obtain this concentration of neutral glycine. In order to do that, we multiplied the relevant concentration by the target volume, giving us 0.1667 moles of hydroxide. Lastly, in order to get the mass of sodium hydroxide needed, we multiply this value by the molecular weight of sodium hydroxide, giving us 6.67 grams.
Moving on, now that we've discussed the different methods of buffer preparation, let's go over some practice problems when conventional methods are unavailable. And so first, we are tasked to prepare 1 liter of a 0.5 molar citrate buffer at pH 4. However, only solid trisodium citrate is present in the stockroom. And so how do we prepare this buffer then? So first, we must analyze the dissociation of citric acid, which is a triprotic acid. And so it has 3 pK values at 3.1, 4.1, and 6.4. And this is a dissociation pattern of citric acid. So the problem is that only one reagent is available, which is trisodium citrate. And so our solution is to use buffer preparation strategy number 4, or using HCl to convert the reagent to the needed species. So to do this, first we need the mass of trisodium citrate needed, which can be calculated by multiplying the volume of the buffer by the concentration of citrate needed and the molar mass of trisodium citrate, which is 258.06 grams per mole. And this gives us 129.03 grams of trisodium citrate needed. Next, we must figure out the relevant species in the solution. And since pK2 is the closest to desired pH, since pH is 4 and pK2 is 4.1, this means that the relevant species are the monoanion and the dianionic forms of citrate. So next, we use the Henderson-Hasselbalch equations to get the concentrations. And so plugging in the pH and the pKa values of 4 and 4.1, this gives us a concentration of the monoanion at 0.2787 molars, and the concentration of the dianion is 0.2213 molars. Next, we must calculate the number of moles of H+ needed to convert citrate in its trianionic form to the monoanion and the dianionic form, respectively. To convert to the monoanionic form, this needs 2 moles of H+ each, which gives us 0.5574 moles. To convert to the dianionic form, we need 1 mole of H+ per mole of citrate, which gives 0.2213 moles. And so the total number of moles of H+ needed to convert all the citrate to the relevant ionic forms are 0.7787 moles. Next, we calculate the amount of HCl needed to generate this amount of H+. So in grams, this corresponds to 28.3914 grams, or if we're using a volume of 12 molar HCl stock solution, this corresponds to 64.89 milliliters. And so to prepare this buffer, overall, we need to first weigh out 129.03 grams of trisodium citrate and combine it with 28.39 grams of pure HCl, or 64.89 ml of HCl stock solution, and mix them in a beaker. This is followed by dissolving in distilled water until completely dissolved. Next, we check the pH and adjust as needed with 0.1 molar HCl, or NaOH, followed by transferal to a 1 liter volumetric flask and adding distilled water to the mark. Finally, we must mix well before use. And so another problem is to purify a certain protein, we need to prepare a 0.1 molar glycine buffer at pH 9.4. However, only a 0.1 molar glycine solution of 9 and pH 9 and 10 are present. And so what volumes of the solutions do we need to mix to obtain 200 ml of the required buffer solution? And so the problem for this one is that both reagents are in aqueous form, as they are pre-made solutions of glycine. And so the solution is to obtain the concentration using pH values, and then solve for volumes 1 and 2 using the final volume as the sum. And so using the modified dilution equation, wherein the molarity is multiplied by volume in the final concentrate in the final solution, and that is equivalent to the molarity multiplied by the volume of each of its constituent solutions, plugging in the values of pH for 9, 10, and 9.4, this gives us the volumes of glycine, wherein the volume of glycine at pH 10 is 0.1338 liters, and the volume of glycine at pH 9 is 0.06624 liters. And so these are our references, and this concludes our presentation. Thank you very much. Once again, we are Group 1.